slideshow set up, and go from current slide. All right. Now the other thing I was going to say, just a reminder, this week has been strange. Today's fairly normal, whatever normal is. Normally, technically, I'm supposed to leave campus on Mondays and Wednesdays at 2. I'd never or seldom, haven't yet, I'll put it that way, okay? So most of the time I'm here 4:45, 5:15, just because I got so much to do. I'm trying to get it done then. However, today I am going to leave a little earlier. I've got someplace I've got to go before they close on the way home. I'm not even sure what time they close, so I'll probably leave around 4 today. So yeah, I'm telling my work study students. Okay. So that is a little unusual. Most of the time I'm here after that, but today I do have to leave a little early. I might be able to get away at 4:30 and still make it. I just don't know what time they close. Anyway, next, tomorrow, normally office hours are 12:15 to 3:15. Not tomorrow, because we have a faculty meeting at 2:30, so my office hours tomorrow will be 12:15 to 2:15, and then I'll head over to the faculty meeting. And then Friday, normally I have office hours 7:45 to 11:45, not this Friday, because it's Veterans Day, so there is no, college is closed, state holiday, no one will be here on Friday. What's that?
If you're leaving at 4, probably won't see you, because I got scholars right after speech.
Oh, you do? Okay.
So probably
Okay. Well, would you want to work later? Because I could maybe go take care of this thing first and then come back. It's here at Vesper. Okay. All right. But anyway, that's this week. Next week, as far as I know, it should be fairly close to normal. I don't know of any appointments or other things that would mess things up. All right. That done, let's move on to, we've covered through 13.5. 13.6 is the last section, and for some reason I can't see my cursor. There it is. No, I do want to just do a quick slideshow of it, if I can do anything quick. Not that funny. Okay. It's pretty neat stuff, okay? Planetary motion according to Kepler and Newton, okay? One reason to cover it is 2 really great paper topics, okay? Kepler or Newton, either one, or how did Kepler go about developing this, and how did Newton verify it or justify it, you know? So there's bunches of possible paper topics here, very much applied type stuff. Kepler had these 3 laws of planetary motion. Of course, this came along after Copernicus, okay, but not really that far after Copernicus. Before that, you know, Aristotle and all the other honchos thought the Earth, and many people still do, that the Earth is the center of the universe, that everything revolves around us, me. Okay, no, it really doesn't, believe it or not. Okay, many things indicated it might, like the sun follows a certain pattern, the moon follows slightly different, but a certain pattern.
It goes over it.
Yeah, and the stars all follow a certain pattern, and it varies some that they couldn't quite account for, but it does do some. And then the planets, they were the problem.
Yeah.
They were called, in fact, the word planet comes from the word wanderer, because they sort of follow a pattern, and then all of a sudden they'll start doing something else, and then go back to doing what they were before. They just get a little wacko. And there's a guy named Ptolemy. I think he was Egyptian, but may have been Greek or something else, I don't know, who went to all kinds of really weird mathematical gyrations to try to justify the planetary motion. And it worked in a very convoluted kind of way, but then it had its drawbacks too. And finally, after Copernicus said, look, the sun is the center of the solar system, and the planets go around the sun, that's why they have sort of weird kind of paths compared to us, because we're just another planet. And I think it was based on that Kepler then started making some really, really careful measurements of the motions of the planets. And I mean, it was complicated because he was here on Earth and having to put together the system with, the focus being somewhere other than the Earth. It was really an interesting thing how he did it. He showed what was happening, but he couldn't tell why it was happening. And that's where Newton came in. Newton, who was born the same year that Galileo died, so Galileo had followed Copernicus, and in fact contributed a fair amount of justification for Copernicus. Whether they ever communicated, I don't know, because Galileo had heard someone in Northern Europe had invented this thing called the telescope, so he found out about it and then started refining it and improved it like tenfold or something like that. I mean, just incredibly better. And he then went out and was able to watch the planets and notice that the planets were not point sources of light. You can look through the most powerful telescope out there at a star and it's still a point source of light because it's so stinking far away. But when you look at a planet through a telescope, you see it has a shape. You see it has phases like the moon does, You can see half and quarter and three or full or whatever. You can see a lot about it. And one thing he saw was Jupiter was spinning. He could tell night to night, and probably not just looking at it, but Jupiter has this one really incredible feature called the Great Red Spot near its equator, and he could see it night to night. It was not in the same place it was, so it had to be spinning. Okay? Not only that, he saw 4 moons going around Jupiter. Wait a minute here. If Jupiter is spinning, and if Jupiter has things around it, then maybe this apparent motion of the sun and the stars and the moon across our things could be not because they're moving around us, but because we're spinning and they're somewhat stationary. Ha! Okay? Yes, this supports Copernicus. And not only that, but if Jupiter has these bodies going around it, then why can't, and obviously we have a body going around us, called the moon, okay? But why couldn't the sun have bodies going around us? That's us going around it, I'm sorry. So lots of things were going on here, but Kepler still, mathematically what he did was absolutely incredible, but he couldn't tell why. So Newton came along, and he was somewhat of a contemporary of Kepler. Kepler may have been a little bit older, but it wasn't like one lifetime apart like it was with Galileo. And Newton said, well, let's see. He couldn't really come up with a full set of reasons why this would be the case, because he just didn't have the math to do it. And it was largely, maybe not totally, but largely this reason that he developed the calculus. Thank you, Newton. Okay, gives us something to study, right? So anyway, quite a history here. So this is more than just, well, yeah, this is really what's going on in the, that was the background for this. Here is one of Kepler's laws of planetary motion. That planets move around the sun, but not with the sun in the center, the sun at one of the foci of an ellipse. An ellipse is an object, if you picture this, now this is magnified. I don't know of any planet that has this elliptical of an orbit. Pluto would have come close, but it's now a dwarf planet. but there's two foci here, and I don't know if you can visualize this, but visualize having a string between these two objects, okay? And as you move the string around, you're tracing out an ellipse, okay? That's what an ellipse is. That's the characteristic, the sum of the distances between the path in the two foci is always equal. So that's what makes an ellipse, okay? Now the center of the ellipse is here. The sun is at one focus. Now for the Earth, the sun's focus is very close to the ellipse, but not right on the center, okay? Other planets are a little, there's actually one, I don't remember which one, it's almost completely circular. I want to say Mars, but it may not be Mars. One of them, almost circular. And the rest of them are typically a little more elliptical than the Earth, but not a huge amount. Okay. So anyway, that's what we've got. So that was his first law of motion, that a planet travels along an ellipse with the sun at one of the foci. Okay. Now the axis that goes through the center and the two foci of the ellipse, that's called the semi-major axis, especially from the center to that edge. The semi-minor would be the short axis that you would have. Perfect issue of that. We're not going to mess with the semi-minor, but that's the other name of that. So here's the three laws of motion from Kepler. Just in case you see something here that you might want to write about, but also just to improve your general knowledge of science and the history of science. First, the law of ellipses. The orbit of a planet is an ellipse with the sun at one focus. That's what I said was first law. Second law. Now, this is pretty interesting, too. And how he did this, just making measurements from here on Earth, you know, all this kind of stuff, how he came up with this, had to have been a really bright guy. Law of equal areas and equal time. The position vector pointing from the sun to the planet sweeps out equal areas and equal times. How did he come up with that? I mean, empirically, he very, very careful, diligent measurements there to come up with that. Okay? And then the third, the law of the period of motion, and that's what the capital T stands for, is period. In physics, I know capital T is usually temperature, but here it's period. The period squared is 4 pi squared. Pi is almost always involved with curved linear shape. Divided by Gm, where G is the universal gravitational constant. By the way, I don't believe that this is exactly how Kepler said it. Basically, he said the square of the period is proportional to the cube of the semi-major axis. That's all he said. He didn't know what that proportionality constant was. How I can fairly confidently say that is that Newton developed this, and Newton, whether it was before or after him, but Newton came up with exactly what that constant was. And M is the mass of the sun, okay? And it gives that value. And G is the universal gravitational constant in SI units, 6.637 times 10 to the minus 11 meter cubed per kilogram per second squared. Strange unit, but true. And A is the semi-major axis, which of course is in meters. Okay. But basically, Kepler's law said the square of the period is proportional to the cube of the semi-major axis.
So, if the sun is at one focus,
yeah,
does the other focus of the ellipse have any importance?
That's an excellent question. I've wondered that myself. I can kind of answer that a little bit. Yes, okay, but I can't really describe to you what it is except for this.
Because the those changes around the sun, would the second foci kind of draw a circle around the sun as it?
No. It pretty much the sun stays fixed, and this goes like this. It doesn't precess that I know of. Okay. Here's what's happening, and this is what that third law was saying. Mostly the second law and the third. But let's just say this isn't a great picture. The second law says the area swept by this in a one given time period. I'm not going to say that's the same. Yeah, it may be. That may be the same time period here. Notice this angle is less than that angle. Okay? But the area is the same because this is further out, so the area is the same. Then this angle is less than either of those, but because it's further out, the area is swept by that. So what this is basically saying, the planets move faster down here than they do over here.
And that makes sense.
And yeah, because they're
gravity
further
is
to the
working
sun.
stronger.
Yes, exactly. There is
Yes.
a component of gravity that's slowing them down or speeding them up. Speeding them up, coming in this way, whipping around there, not that much. Because really, the sun is much, this is an exaggeration here. Like I said, Pluto might be this bad, but that would be about the only one. But this is just so you can see it. And then how in the world did Kepler make this careful of measurements that hard to make and come up with this? But pretty clever guy. That would be worth a paper topic there. Okay. Now, what I was going to say, I may be getting some of these names wrong. I don't think it was Laplace, I think it was Legendre. It was one of the, I think, French mathematicians that if a focus is here, then there is something that aggregates around the other focus or at certain intervals around there. And I think there is some significance, but I just can't fully define what that significance is.
I wonder if it has, I don't know, it's paper top.
Yeah, that I was just going to say it might be worth investigating for a paper time. So those are the three laws of motion, Kepler's laws of planetary motion. Here is a better rendition of what I was trying to show before, because this is taking far bigger wedges than what we had before.
As you get further, your angle decreases.
Right, exactly, because the area has to stay the same. And so the area swept in a given time here, same given time here, so obviously the planet is moving much faster here than it's much slower there, but the area is the same here and there. How in the world he was able to do that? I mean, how he was able to even measure the distance from the sun to that planet and that one, same planet, and do that for several planets. He was a pretty good guy. I mean, pretty good. The two shaded regions have equal areas by Kepler's second law. The planet sweeps them out in equal times. And that has to then be related to the third law, which relates that time, the period, with the semi-major axis.
Kind of reminds me of when you have like a long string connected to a ball or something. You spin it around, and as the string gets shorter, it starts going faster.
Right, exactly. Yeah, that kind of a thing. Exactly, that's what's happening. So I think we beat that one to death. Okay.
Yeah. Too bad
All
it's
right.
not horse.
Now, here was the kind of thing, I think, I'm not sure on this, so you can research it if you want to. This is how Newton then took the data, the information, the observations that Kepler had, and put it into mathematics. Of course, he had to come up with derivatives to do that. Okay, he didn't have derivatives before. This is why I think one of the big impetuses for developing the calculus, so he could describe it. And this says that the second derivative of the displacement vector, which, by the way, is the acceleration vector, is equal to some constant k over the displacement vector magnitude squared minus that times ER, where E is the unit vector along the radial. Okay, so if the sun is here. here, and the, let's see, do you do it from the center? I think it's from the center. And the planet is there, then the unit vector would be the vector pointing from the center to the planet with the unit length. The minus sign means the acceleration is inward, okay? And it also says this is the magnitude of that acceleration related to that k over t. Now, do they tell us what k is? Kepler's law. Oh yeah, k is that gm that we had before. The product of the universal gravitational constant times the mass of the sun. Okay. So that's the k. Okay. Now, and I was wrong. Okay, here's the picture, I hope. Yeah, I said the center, but it's not the center. It is the sun. I couldn't remember if it's the focus or the center that you measure that vector from. And this picture clearly shows it's from the sun, or the foci. So there's ER pointing toward the planet. Minus ER will be pointing from the planet toward the sun. And that force vector, again, forces, that kind of stuff came into play, related to, proportional to the acceleration vector. Acceleration vector, we're just looking at magnitude of that, and is the mass of the planet times k, which is g, the mass of the sun, divided by, what was it, 4 pi, whatever that constant was. So the gravitational force directed from the planet to the sun is the negative multiple of the unit vector from the sun to the planet. And if the force is in that direction, the acceleration is in that direction. Okay. Now, this introduces another concept that I don't think we've hit before, but you probably will see it again. The key to Kepler's second law is the fact that the following cross product is a constant vector, even though both r of t and r prime of t are changing with time. It's a constant vector, and I'm trying to find the name for it. Do y'all see anywhere where they actually name what J is? Oh, there it is, angular momentum. Okay, I knew it was, but I said they better say it. It's over on the side margin. In physics, mj, not J itself, but mj is the angular momentum. In situations where J is constant, we say the angular momentum is conserved, and that conservation law is valid whenever the force acts in the radial direction, which here it does. Okay, so this isn't exactly angular momentum, but it's the product of the mass times the angular momentum, which would then beg you to almost say this is the angular speed. Now, I'm not sure that is true, but it seems like if the other two statements are true, that would have to be angular speed. Surprising they don't say that. If it were that, it seems like they would have said it. All right, so here's J. Now, you'll run into this concept in other places as well, but here is a pretty important thing too. Now, and that relates very closely to what you were saying about the speed of something going, because the angular momentum is constant, but the radius is decreasing, so the speed is increasing because this is constant. That's the same thing with the figure skaters doing the spin, and then when they wrap their arms in, they go really fast because their moment is decreasing. So you'll run into this again if you take statics, dynamics, that kind of stuff. All right, from this rendition, then we also have this one. A theorem has to do with Kepler's laws of planetary motion, but it has to do with other things. The vector J is constant, planetary motion, meaning that the derivative of J with respect to time is zero vector. Okay, this would be if and when you run into it again, you've seen it here. Now, all right. The orbit is contained in the plane orthogonal to J. Okay? If you remember back your binormal vector, if your velocity vector is in one way, or unit tangent vector in one way, the unit normal vector in another way, the binormal vector is perpendicular to both. Same type of a deal here. Your displacement vector this way, your velocity vector that way, that means, because it's a cross product, the J vector, just calling it J, I wish they'd give it a name, is orthogonal to both. Okay? And of course, we have not shown that the orbit, is an ellipse. That was the first law. We haven't proven that yet. And again, they're greatly exaggerating these. Most of the planets are far less elliptical than that. They're closer to being circular, but none of them are exactly circular. One is close, but not that close. And by the way, if this were Earth here, where would you guess, what time of year would you think this closest point, which is called, see, I always get these crossed up, apogee, and the farthest is perigee, or vice versa. One of them's one and one's the other. I just don't remember which is which. What time of year would you think they would be? Which?
The one that's closest to the sun.
The one that's closest to the sun is in winter?
Yeah, because they're still.
Okay. You're absolutely right. It's around January the 4th or 5th, something like that, is when we're actually closest to the sun. And when we're furthest away, somewhere around July the 11th or something like that. Yeah. Well, our temperature is mostly affected by the tilt of the Earth, not by how close. Now, two things here. The distance is not that great. Okay. But the other thing is, it's the tilt of the Earth that makes it. Now, think about poor southern hemisphere. When they're farthest away, that is the middle of their winter, and when they're closest, that's the middle of their summer. Okay. What's that? Yeah. So they should have, I've never checked this to see if it's true, maybe a good paper topic, do they have wider variation in extremes of temperatures than we do, because we're counter that. We're tilted toward the sun when we're furthest away, and tilted away from the sun when we're closest to the sun. And that should moderate our extremes of temperature. Whether it does or not, I don't know, but it should. Okay, side point, but it just happens to be true. All right. Boy, there's a lot of slides in this section. And again, you're not responsible for it, but I thought it's important enough science and application of mathematics that you need to see it. So let's let the magnitude of J be J, okay? And that is constant by theorem 1. And then what would that magnitude be? Okay? Well, this follows from the other definitions. I don't want to go back and do those, but here's what it is. This is, I wish they put the square here. It's the square of the position vector, the magnitude of the position vector, times the angular speed. That's d theta dt, okay, how much that is changing, which usually we call angular velocity, okay. Now the angular velocity really has no units for, it's per time, it's angle per time, so really what the r squared then gives it a velocity-like vector, because one of these r per unit time would be like a velocity, and the other r times theta would be the arc length. Okay? So basically it is how fast it's moving around. Okay. Now, going back to those unit vectors that we sort of mentioned, we only mentioned E sub r, but if you have your length of your displacement vector, magnitude of the displacement vector, little r of t, not vector, but magnitude of that vector, and your radial vector, which is from the sun to the planet, the unit vector in that direction always, and this is cosine theta sine theta, meaning the x component of that is the cosine of the whatever angle you have, and the y component is the sine. Okay, you would have thought that was a circle otherwise. Okay, if this r were constant, then it would have been. E sub theta then is the unit vector that's basically like our tangential vector, except it's the unit vector in the theta direction, and that's minus sine t cosine, minus sine theta cosine theta. And obviously, or I hope obviously, you see if you did a dot product of these two, that would give E minus sine theta cosine theta plus sine theta cosine theta, that would be 0. What does it say for the dot product to be 0? They're orthogonal to each other, absolutely. So these are at right angles to each other. So they form basically a moving coordinate system that's rectilinear, right angle. Okay? So let's see if we can zoom in on the picture of that. Illustration of that, I guess, would be a better way to say it. So the unit radial vector is pointed toward the planet. The unit angular vector, you would say, theta vector, would be perpendicular to that. And if you would take this and move it out here, that comes awfully close. In fact, I would say exactly to be the tangential vector at that point right there. Unit vector E theta and ER and E theta are orthogonal to each other. We saw that before. They rotate around the origin along with the planet. So what they're saying is the planet moves in this right angle relationship moves with the planet, like that. Or if you put them kind of out here, then probably better there. And by the way, the J vector would be coming perpendicular this way. So almost an XYZ type arrangement. Now, a few notes about them, especially if you went back and did the vectors themselves. Remember cosine theta, sine theta, that was this one, right? Take the derivative of that. I don't have it up here, it's down in my office. So let me pause this just a minute. I'll run again. All right. I'm going to write something on here. It'll be up there before I get it written, I think. Okay. Remember remember what ER was? Unit vector in the R direction was, remember what that one was? Yes. And what was E sub theta? Yuck. I know, but it would be ugly. Okay. Who minds ugly, huh? I got y'all in. No, I didn't say that. Okay. E sub theta.
That would be negative sine.
Negative sine theta. Cosine theta. Okay. And what's that? Exactly. That's the point here. Derivative with respect to theta of e to the r is? Yeah, just what you said. Minus sine theta. Derivative of that would be cosine theta. And that would indeed be e to the theta, e sub theta. Okay? This is e prime. And this happens to still be a unit vector, strangely but true. Okay. And the other way, if you did dE theta, so dE theta, I'm really mixing up my symbology here. Okay. What would that be? Negative cosine theta, negative sine theta, which is minus ER. I drew it on the wrong place. Minus ER. That's supposed to be an R. Yeah, unit, yeah. Okay. All messed up. So you see these are indeed true based on what we were calling them before. That's indeed true.
At least they're not in regular parentheses.
Yeah, well, this book's using the right one, okay? I may not always, but it is. Okay. That's what I was trying to do.
Not the left one.
Okay. I don't have it all on there, but you get the general gist of it. Okay. So that's nothing too new. Now, let's see if this is anything worth illustrating. Another thing you could say about der d theta, okay, would be that was, no, I'm sorry, der dt, that would be d theta dt times der d theta, chain rule, right? Okay, well, d theta dt, that's e theta. That was our other definition of e theta, and this is, I'm sorry, that's theta prime of t, and this was our e theta, okay? Derivative with respect to e. So e prime, this is with respect to time now, of the first derivative of your unit radial vector with respect to time is the derivative of your theta vector times e theta, because that was our e theta. Okay. Let's see what else we can draw from there. dv dt, which is change of velocity vector, which would be dr prime. Oh no, that would be r prime of theta. Yeah, r prime, which would be dr. Second derivative with respect to time of your r vector, which is first derivative with respect to time of your velocity vector, which is your acceleration vector, and that would be minus k. Now remember that k? G times L. G is the universal gravitational constant known as the mass of the sun. And I think we had that somewhere in the past, several slides ago, when we called it the acceleration vector. Seems like we did. Or we call it second derivative of the r vector. Okay?
And how they move the mass of the sun.
Yeah, well, that's because we're dealing with our solar system here. Some other solar system that work for their mass of their sun, you know. All right.
I mean, it's like figuring out what the mass of the sun
Oh, yeah.
is kind of interesting for way back then.
You got that right. Okay. How those guys did it, I mean, it would almost be worth reading and studying up and saying, how did they do that? Okay. Now, if you took that previous differential equation we had, which is what it was, dv dt, we needed d theta. Sorry. I think there's a lot of stuff in between where we were at that. So I don't think we can do too much with that right now, except obviously we can integrate this if we get that. And that would then be, this thing here is our e theta. There's a lot of ground between where we were and that one, okay? Now, I want to say maybe I misled Cameron in something that he was saying. There must be a little bit of precession type stuff going on. That the perihelion, which is the closest place of advance, yeah, that,
to the actual path.
yeah. So it does do some of that, not a very rapid, but the perihelios of the orbit shifts slowly over time. For Mercury, the semi-major axis makes a full revolution approximately once every 24,000 years, okay? where that thing can go all the way around like a Etch-a-Sketch. You know, what do you call those?
Slinky.
Huh? No, the things you have little dots you put your pen in and you follow the thing. And
I don't know what you're talking about. I don't know what the name of it is, though.
But if you
it's
did
like
that.
It's a plastic thing you hold down.
Exactly.
And you do different.
Right. It would go around once every 24,000 years.
I knew there was some movement. I didn't know how.
Yeah, and there is some. You were right. It's just a very slow movement.
It seemed too good to be true that it would be all one plane.
Yeah. Well, and they're not really quite all in the plane. All of them have a little
like
different angles.
Each one, but
right.
still, that's 3 space, you know?
And all sorts of things can happen with that too, other perturbations. And by the way, Mercury, of course, being the smallest thing, it's going the fastest of any of them, and it does this every 24,000 years. How long does it take Neptune? That would be hard to imagine.
That would be interesting.
Yeah.
But I don't know, maybe, let's see, since that changed.
What's that?
But gravity affects it different. I don't know.
Yeah, all sorts.
Maybe the swing affects it more and causes it to advance quicker.
Yeah, could be.
Per rotation.
All right, and we're back almost where we began.
Yeah, because that's the summary. That's the same picture from before.
Yeah, that's your planetary motion. I think the very first slide we saw. And that was it.
Into astronomy.
Yeah. There is a little historical perspective at the end of the section that covers the Hubble Space Telescope, which would be a paper itself. Yeah.
They just finished a newer inventor.
Oh, really? But it's not been launched yet, right? Or has it?
It's still on the ground.
Yeah.
It has like gold-plated mirrors or something like that to help with that accuracy and to get rid of some of that kind of fog or whatever.
Right.
Really neat.
Is that going to be the Trump telescope? No, I didn't say that. Okay. Seems like he does everything and never mind. Okay. So guess what? Just by that, Hubble would be a potential paper topic. The new telescope could be a potential paper topic. The you could do anything based on what you've gotten from the Hubble Space Telescope and stuff. As you look at this, I've already mentioned the name Copernicus, but you could talk about any of the other astronomers in ancient world, Babylon, Egypt, and Greece. Aristarchus, one of the first ones to suggest Earth revolved around the sun, kicked out. He was an idiot, right? Yeah. Then Copernicus, then Tycho Brahe, I don't know, Galileo Galilei. Okay, Johannes Kepler, and just reading this, you can come up with how many different paper topics could you get there? Newton's law, so there's Newton, Albert Einstein, his general theory of relativity, Einstein field equations, and by the way, Mercury's perihelion shift was accurately explained by his new theory, by the way. And also, I don't know if y'all have been following this, but there happened to have been a collision of 2 black holes, I believe, that happened in the last few years. I don't know when it did.
It happened earlier this year.
Earlier this year,
Maybe
okay.
even last year, but I think it was earlier this year.
Well, okay. In reality, it happened an awful long time ago, but we got to see it this year, okay? And that event itself has given credence to one of Einstein's theories on gravitation, that it actually was less force at a distance than actually some type of a, I'm using this loosely, fabric that made up that. That itself could be a potential paper topic. Incredible stuff there. Okay. Yes, sir. Oh, I'm sorry. I meant to open that door earlier. I thought I did. Maybe someone closed it.
Yeah, it's a James Webb Space Telescope. It'll be Hubble's successor.
Right. Okay. And James Webb could be a paper topic. Who in the world was he? Obviously an astronomer. All right, and by the way, yeah, that's it for chapter 13.
Because technically that's the telescope's name.
What?
That's the telescope's name.
Yeah. Oh, okay, yeah. We decided to name ourselves James because that was my great uncle's third name. Yeah, or whatever. I don't know. Anyway, before I forget about it. What's that?
Come from a long line of telescopes.
Yes, exactly. Okay.
My great-great-grandfather was just a lens.
Yes. Actually, there was actually a physicist named Lenz. Lenz's law. It's in electricity. Okay. Here we have test 2. I know y'all were demanding it. This is on chapter 13, I believe.
Yes, we were demanding.
I get 2.
Your other compatriots is in. All right. Let's move on to chapter 14, which...
This was purely chapter 13, right?
Yes, that's... Oh, and I'll go over. The first 2 questions is 13.1. Next 2 are 13.2. Next 2 are 13.3. The next 2 are 13.4. And the last 2 are 13.5. 2 per section as you see them. Should have said that earlier. Okay, so let's move on to chapter 14. I probably took too long with 13.6, but it's such interesting stuff. What's that? I know. So sad. Okay. And the National League had won the World Series in 7 games. And the Reds, well, yeah, but they ended in a tie. Yeah, okay. So, I know, I didn't know pro football had ties.
I didn't. And at this point,
Yeah, I knew the managers were, no, I'm just kidding. Okay. And frankly, I feel like chapter 14 is one of the key chapters in Cal 3, and we're just now getting to it. So hopefully we can get through this pretty quickly.
we only have 2 weeks.
I know. So let's get through as much as possible because this is key. And really the one that follows it, integration in several variables, or multiple integration we call it, that's also pretty important. I wish I'd have taken less time at the earlier stuff than what we have now. And sometime another this should wrap up here.
How many sections is in 14?
It looks like maybe 8 or something like that.
That's great. I don't know if
We won't do them all. Yeah, it looks like 8. What's that?
Chapter 14 will be the final, probably.
Yeah, it probably will be your final exam. Wait, yeah, from current slide. All right. Pretty picture here, not in my book. But this is the famous Triple Peaks, Eiger, Moik, and Jungfrau, or something like that, in the Swiss Alps. The steepness of the point in the mountain range is measured by the gradient defined in this chapter. Okay. Yeah, I wonder if it is. I don't know. Maybe it's a smaller one. I don't know. So, I wonder. Okay. They show a mountain climber in the new text going up a pretty steep gradient. Wow. Not me, folks.
Nearly sheer.
Yes. Too sheer for me. Okay. Then there's this figure. Also, this is in our text, the new text. Don't know which one y'all have, but it's in both of them, most of the last 2. This is global climate is influenced by the ocean. They call it a conveyor belt, a system of deep currents driven by variations in seawater density.
That's pretty awesome.
Yeah, it's really amazing. And notice this is all, yeah. Okay.
This is kind of general.
Yeah, very general. Now notice this is going opposite to the surface current, at least in some places, because here you have the Gulf Stream that goes up like this. That's the surface. These are the deep current conveyor belt. Now what this does, it obviously seawater density, so this is mixing the salinity. It's also mixing temperatures, because really deep, I was shocked to hear this. I've always thought of the Gulf of Mexico as a warm bathtub. I mean, it's very warm water. But when they were talking about the Gulf oil spill, which was in the Gulf of Mexico, of course, it was about a mile down, approximately, maybe a little more. They said it was very close to 0 degrees down there. And I thought, my words. So yes, you go deep enough, you're in very cold temperatures. Okay, and
lack of light.
Yes, exactly. That's it, exactly. So
Unless
this is deep stuff. This is not the surface thing.
Unless there's geothermal energy, like volcanoes,
Yeah, exactly.
Then
And,
that would make sense.
and you could anticipate some of that up in here, because this is where the mid-Atlantic Rift goes. And Iceland is somewhere right about there.
And also, don't they have like a big circle out in the Pacific?
Yeah, well, yeah. This is called the Ring of Fire.
Yeah.
Yeah, and the Hawaiian Islands, the Marianas Islands, all the island chains that you have out here are volcanic islands. So you have those going on as well. Some of those are very deep. Marianas chain, in fact, deepest point is in the Marianas Trench. So yeah, there's all sorts of things governing this, but this is pretty interesting, especially the fact that they show this crossing right through Indonesia here, which would be sort of interesting because these are islands. Okay, how does that deep current go through the island?
It just goes around.
Huh?
It just goes around.
Yeah, I guess so. Okay, so that would be sort of interesting.
Isn't a detailed enough map.
So the point for both of these is that you have more than 2 degrees of freedom. You don't just have dy dx anymore. You have, in this case, you have seawater density depends on salinity, it depends on temperatures, then you have 3-dimensional motion going on here. So you have bunches of degrees of freedom, not just y depending on x. Same thing with the mountain climber. He can fall this way or that way or this way, lots of degrees of freedom there. And then the third picture here is not quite like mine is, but this is.
They're similar.
It's very similar.
Looks like the same caption.
Yeah, I wouldn't be at all surprised if they aren't, but it's the talking about the same type of thing. This is the conductivity temperature depth instrument, which they use to measure that seawater density. So I left that one out. I mentioned temperature. I didn't mention temperature and salinity. Salinity is related to conductivity, but then depth is the third dimension there. And then you also have the lateral dimension as well. So, and then this other variables, density, temperature, pressure, salinity. How many variables you have here? How can we deal with all those variables at once? That's what this chapter is dealing with. Okay? And sometimes when you're doing this, you have to have multiple dimensional tables, like you have parts per million going that way, parts per thousand going that way, degrees going this way. And whatever you're measuring, the density going that way. So you have one independent variable with 2 dependent variables. Density depending on salinity and temperature. Okay. Well, what are we meaning by that? Here we're going to imagine, now this is 2 different things here. This is your good old XY axis that we're used to living in 2 space. Okay? A parabola.
We missed example
Oh, and this is example 1?
1. It looks like
All right, let's do the example 1 then. Well, let me just go through this then. This is your what we're going to be using as a domain of this function here. F depends both on x and y. It's not that F is y. Those who you had pre-calculus under me, what I harp at that class all the time is, remember this, y is equal to f of x. I just say that over and over. We can't say that anymore because now f of x, y is some other function.
Y is independent. F is still
X and y are now independent, and your f of x, y is now your dependent. Okay? So this then forms a domain. If you're using the things inside this is the domain for, say, the function z that is somewhere out here. Maybe is a pup tent over this or something like that. All right? And there's another one. We'll get to that in a minute. Let's go back then and do example 1. Sketch the domains. That is the domain of that.
What are the range of these functions?
Okay, and then what would be the ranges of the function of the a function there? If this was your domain, that was everything inside this parabola, f of x, y is equal to square root of 9 minus x squared minus y squared. You could write that as 9 minus some of those squared, They left off the square there. No. That is a y. That's a problem. So it is a y.
So,
What would be the range?
well, x could be
Okay, x could be anything,
anything.
positive or negative. But when you square it, it's going to be positive. So, sure enough, this has to be there, but it can't be a bigger number than 9. X squared can't, because then you'd have a negative under the parabola. So that's why we're limited to the parabola. You can't have values out here.
And y can't be bigger than
9.
9 plus.
All right. And if it is 9, x has to be 0, because otherwise you have your thing to be that. So what about the range? What is the stuff that depends on f of x, y? What is the possible values here?
9 to negative infinity.
Okay, definitely not negative infinity, because this is a principal square root, meaning only positive. It can be 0.
Well, if y was negative, you're adding it.
Okay, now y is an independent
Yeah,
variable.
we're talking about that.
We're talking about f, range of f. Okay, range is no longer y.
Yeah, range is no longer
Your
y.
domain is something in x, y. That's why it says parabola. So your range is what f can be. What can f be? As you said before, it can be 0. If x is plus or minus 3 and y is 0, then this would be 0. If y is 9 and x is 0, then that could be 0, but everything else has to be inside here. So these are all numbers from 0 to positive infinity. In fact, I guess it'd be positive.
The outcome of
Yeah. Because basically it's a principal square root.
you can't have anything
Only
less
positive.
than 0.
Yeah, exactly. You can't have 0, but you can't have anything less than 0. Good.
Because if you
Okay.
do that, introduce imaginary numbers, you don't.
What's that? Yeah. Okay. We're not going there. We're going to stay real for a bit. Okay. Here is another function, g of x, y, and z, all those being independent variables, where that is x times the square root of y. I don't know if you can read that. Let me blow it up maybe to help you read it. We'll shrink back down when we go to write on it, if we write on it. Okay. X times the square root of y plus log of z minus 1. So there's your function. Now it says what's the domain of that? Those would be the acceptable values for x, y, and z. X can be all real numbers, right? Y can be Yeah, 0 or positive, non-negative numbers. So the y's are all, it can be 0, but everything to the right of that. Nothing to the left.
And
X can go both ways. And what else? Z could be what?
Z, let's see, it has to be less than, I know it.
Greater than 1. So log, you can't take the log of 0, you can't take the log of a negative number, so Z has to be greater than 1.
Right.
So Z, you can't see it here, but you've raised this base up at 1. That's the foundation here, but it's not on that base. It's not on Z is equal to 1, it's everything above that. So that's a dotted base, okay? You can't be there. You can be Y is equal to 0, and X would be anything, but the Z is only greater than 1. So that's your domain of G. What's your range of G?
Okay, let's see. Well, X can be anything.
X would be anything.
So X times the positive number is still going to be a positive number.
X would be anything, plus or minus.
Oh, yeah.
So
Well,
this product can be,
Look at 0 first. You would end up with a natural log of -1, which would be okay.
okay,
Maybe 0.
what's this down?
If 0, that wouldn't work.
It won't work at 0, it won't work at 1. But just past 1, you're infinitely negative. And then way past 1, you're infinitely positive. Log goes from here to there. Its range is that. So this has a range negative infinity to positive infinity. That has a range negative infinity to positive infinity. So I think the range of this is all real numbers. Okay?
It could be.
Yeah. There's no restriction.
It just depends on what X is, really.
Yeah, it depends on X and Z. Y is just a multiple. Okay. Good deal. Thank you. Okay. Do they answer that? They say to determine the range that in the first one that f is non-negative function, blah blah blah. Since y can't be a positive number, it takes on all non-negative values. Therefore, the range of y is from 0 to positive infinity. That's what we said. Range of f. G, we said G takes on all values. Exactly. All right.
The range with increased space is variable. The range period with this is kind of strange.
Yeah. It's the values of your output.
Right.
And the output here varies on 3 independent inputs, or 2 on the first one. All right, graphing functions of 2 variables. I think this leads to example 2. So let's do example 2. Now, do any of these figures relate to that? Yeah, I guess they do.
It just skips the graph.
Yeah. Actually, this figure doesn't relate to 2. This relates to the wording before that. I think all they're saying here is a graph, y is equal to f of x. Okay? This is what we're used to in 2-space. This was Cal 1. This was probably Cal 2. You know, this is what we've lived with before. Y is equal to f of x. The input is your x, the output is your f of x, which is in this case y. So there would be it. You can talk about relative maxima, relative minima, turning points. You know, you can talk about all those kinds of things. Okay, there's your graph there. This is in 3-space. Z is some function, or f is some function of a and b, where a and b is defined on 2-space, x, y plane. So a, b is down here, and then your function f is somewhere up there. Okay. Well, you can also talk about sort of some relative maxima, relative minima, places where the function's not changing much at all. You know, so you can talk about a variety of things there, but you've got 3 dimensions to work with here. You basically only have 1 to 2. Okay? Now, this was a shape like we did in 12.6. Anyone remember what we called that?
That would be a cone. No.
No.
A cylinder. No.
A what? A what? I can't hear.
No. Cycloid was the thing that went like this.
Okay.
This is something that's usually like an hourglass shape, but now it's been cut in half to one sheet, right?
Okay, you're closer, but this is, what would this shape right here look like?
It's a parabola.
A parabola. So this is a paraboloid. What kind of paraboloid?
It's
What are those cross sections?
ellipses.
Elliptical paraboloid, exactly. The other kind was hyperbolic paraboloid, which is
That's
sort of
what-
like that saddle
Yeah.
point. Yeah, okay. This is your elliptical paraboloid, okay? Because your z here, you might think of this as a function of x squared or y squared, but this is not squared, so this is, yeah, that. This would have a major axis on the y. I'm not sure I can see that well. And the minor axis on x, is that right? I may have said this backwards, but anyway, you see that's what
Looks like
makes
the major
it
axis is x
Yeah.
and the minor is y.
Yeah. If you look at this for any constant here, 0, of course, it's just going to be 0, 0. That's the only thing it could be. But say 1 here, then that would be an ellipse. Okay? And this would be an ellipse with 2 or 3 or 4, whatever. So yeah, those are elliptic paraboloid. Okay. Now, I think we're ready for, this is example 2. Sketch the graph of, they're going to do it for us, thank you very much. Sketch the graph of f of, oh, here it is. No. I'm sorry, that was the last one. That was figure 5. Sorry about that. This was figure 5 right here.
No, we just answered their question.
I did, yeah. Okay. That was our sketch the graph of this thing, and there it is. They've sketched it for us. The graph is a paraboloid, which we saw in 12.6. Yes, okay. We sketched the graph using the fact that the horizontal cross sections, called the traces, are all ellipses above the y-axis anyway, and so every one of those is an ellipse, but the vertical traces, slices in the x-axis or slices in the y-axis, that would be, say, x-axis, that way would be z is equal to something x squared, that's a parabola, or y, this would be z is equal to something with y squared. And if you let these come out and back, then you have constant stops that move up and down the x or y axis. Okay. I guess that's all we had to do there. They plotted it for us. Thank you very much. Now, what I'm trying to see is where figure 6 is. I see figure 7. Oh, there it is, bottom of the page. Plotting more complicated graphs by hand can be difficult. Talk about understatements, okay? Fortunately, computer algebra systems eliminate the labor and greatly enhance our ability to explore functions graphically. Graphs can be rotated, viewed from a variety of perspectives, and that's what they've done here. Now, again, I will start here and work my way over. Here is z is equal to e to the minus x squared minus y squared minus e to the minus x minus 1 squared minus x, e to the minus x minus 1 squared minus y minus 1 squared. Whoa, okay. Now, let's just see if we can get a feel for what this is doing here. This first part, I would be tempted to say that is e to the minus parentheses x squared plus y squared, which makes me think of a circle kind of, okay? And e to the minus is going to have a certain dipping to it. whereas this one looks like minus e, or subtraction from that, e to the, this is something offset 1 on x and 1 on y. So I would contend this corresponds basically to this hump, okay? And this one corresponds to x equal 1, y is equal to 1. Its center is at 1, 1. Ah, good, Jonathan's here. What's that? Yeah, let me get it. Okay, I've got to dig through and find it again. Not much further now. I think that's it. All right, and again, I'll go over 1 and 2 are from 13.1. Okay. Each two of them is from another section. 1 and 2 from 13.1, 3 and 4 from 13.2, 5 and 6 from 13.3, 7 and 8 from 13.4, and 9 and 10 from 13.5. Right. All right. So I'm pretty sure that that's what this is. This corresponds to e to this part, and this over here is corresponding to e of that part. Now they twist that around so you're looking right down x, y, and you can see this is pretty much around z, which fits this description, and this is pretty much there. Now, this is positive here, so that's going upward. This is negative here, so that's going down. Just little things you can do. Try graphing that by hand. Good luck, Jack. Okay? Hopefully you can get an algebra system to do it for you. Okay. Now, I think this is what the next part is. This first section is a lot more ooh-wah type stuff, you know, oh, look at this, you know. Not too much that you're asked to do. I mean, we did have a little bit. One way of analyzing a graph of f of x, y is to freeze the x coordinate by setting x equal to a, which is what we've been doing when we did the vertical traces. That's exactly what we did, or y is equal to b, or something like that. And examining the curve z is equal to alpha of not xy, but ay, when you set x equal a, and doing the same from y is equal to b. Looking at z is equal to alpha of xb. Those are vertical traces, like we were talking before. They are obtained by intersecting the graph with planes parallel to the vertical coordinate plane, either xz plane or yz plane. Okay. The vertical trace of a graph at x equal a is the intersection of the graph, the vertical plane, x equal a, and consisting of all the points that are on that. So I think that's what they're trying to show here. This is not quite the same graph we had before, but you know, something like it. You have a hump here, a depression there, and another hump going back that way. Okay? Now, if you do x equals some constant, for instance, x equals 0, that would be the yz plane there. That would probably be, if I'm looking at this right, probably not. Oh, would this be it? Would that be right there? Looks like that could be it. Okay? And as you come further this way, it's a curve like that, or a curve like this, or a curve like that. You know, going back that way, you have a curve going like that, one going like this, one going almost flat, another going like this. Those are your x equal constants, whatever they are. Vertical plane traces parallel to the xy plane. Now that same curve, hump over here, depression there, hump here, okay, do y is equal to various values. Now, if I'm looking at this one right, it looks like this may be y is equal to 0 right here. It's going somewhere down there. I'm kind of losing it. It's hard to keep up with that. Maybe it's that there. And if I come this way in y, then there's the next one. There, it's hard to see that too. Maybe that's part of it, and then it comes up maybe here. And then the next, this one looks like y is equal to b out here, so that's going like that. The next one out would be like this, so the next one out like that. That's where that came from. Or if you go y is negative, you can have this curve back here, and here. You can't quite see which one they tie to, so that they come up somewhere over there. So those are your vertical traces on that y is equal to, parallel to the xz plane. These are parallel to the y plane. Those are your vertical traces. In this one, they didn't show horizontal traces. That would be your parallel to the z, xy plane going up or down z. Now, it's sort of hard to see here, but you can imagine up here you get two circles here and nothing else in between. Down here you get a little bit more, and way down here you just get circles or ellipses or something down there. So, have any of you ever seen a contour map? Yeah, contour maps are horizontal traces, various levels. Okay. I think this is example 3. All right. Describe the vertical traces. No, this is example 4. They have an example 3 in here, but I don't see the picture in the slide. There it is. I guess when I went to hit it, it disappeared. This is, I think, example 3, which looks more difficult than example 4 right off the top. Okay, describe the vertical traces of f of x is equal to x sine y. Describe the vertical traces of f of x is equal to x sine y. All right. Well, obviously, when x is 0 and y is 0, z is 0. So that point right there is the origin of those three, intersection of those three graphs is 0, 0, 0. Now, when x is 0 anytime, that would be anytime on the y-axis, then it doesn't matter what y is, z is also 0. So therefore, this line here, the y-axis is on the graph, everywhere. Now, what if x were 1? And that's just a sine curve. Y is equal to, and that would, now, x equal 1 would be out this way. This is positive this way. It goes from the x-axis up and down and up and down and up and down. So you get this wave-type motion there. And if x is equal to 2, what you have is another sine curve, but now the amplitude is 2 rather than 1. Okay, 3, 4, 5, and so on. You just keep getting sine waves that are getting bigger and bigger and bigger, but they're very uniform sine waves. Also, if you're going backward, x equals -1, now your sine wave goes down to -1 before it comes up to +1, goes up to +1 before it goes down to -1, because you have a negative. The amplitude is still 1, but it's a -1, so it means it reverses everything. Same thing for 2 and 3. So this hill goes down to that valley, this valley goes up to that hill, and so on. So that's your general description there of your vertical traces at x equal a, various values of it. At y equal a, okay, let's say y is equal to 0. When y is equal to 0, guess what? You're right down the x-axis again. Because the z doesn't go up or down, because sine of 0 is always 0, no matter what value x you have. Now, what if you come out y is equal to, say, 1, say? Okay? Let's not say 1. Let's say y is equal to pi halves. Okay? That would be a pretty good movement. The sine of pi halves is 1. So then that would be z is equal to x. So now you have a line that is in the xz plane XZ plane, the line x equal 1 is this one here, okay? Because it's negative when x is negative, positive when x is positive. So x is positive this way, negative that way. There is when y is equal to pi halves, so that's probably pi halves, you got a line like that. Whereas when y is equal to pi, 0, so here you have another one parallel to the x-axis there. You have one there. Stays 0 everywhere. But when y is equal to 3/4 pi, right? 3 has pi. Now your sine of 3 has pi is negative 1. So now you have z is equal to minus x. So that means when x is positive, z is negative. When x is negative, z is positive. So that's the line and stuff like this. So that's kind of what I was describing here. The valleys going down, the valley going up, down, up, yeah. That's what these lines are doing here. They're right on the peaks. In between, you got other mess going on. So that's exactly same graph. That's the description. I just chose the ones that are easy to work with. You can choose any of them. This is the easy one to work with. Does that make sense? All right. And that's what they asked us to do. Describe the vertical traces. We did. All right. Here's example 4, I think. Let's see if I can blow this up. Okay. Identifying features of a graph. Match the graphs in figure 9 with the following functions. Okay. Shame on them. They already done it, haven't they? All right. Boo hiss. Okay. All right. You can't read over my hand. Okay. How would you describe that shape there? Can y'all see it? It's parabolic in shape. It sure looks like it. Okay.
It's kind of going diagonal along the x-axis.
Okay. Well, now this is the x-axis.
Yeah.
This is the y-axis. Okay. It looks like to me this parabola is dipping below the here. So this would be.
What I was saying is it's kind of following the x equal y kind of path. That line.
Oh, I see.
Yes,
okay.
That's what
the reason I sort of doubt that would be coming down here, and that's not quite. I think this is supposed to be centered on y. I'm not sure, but the appearance is.
Well, I just changed the way I'm looking at this.
Yeah, that's what you're looking at. Trying to look at a 3-dimensional drawing in a 2-dimensional board. That's hard to do, but I think this is a parabola with y going right through here. The parabola right here, I think, is, let's see, z is equal to x squared, okay? And if you come out this way, what you're doing is you've got a vertical shift downward, negative z, so that's happening, but your basic shape looks like it's staying the same. So it's probably still going to be, I'm going to say y minus something is equal to, did I say that right? Y is equal to x squared. This would be z is equal to y squared. So this would be z is equal to y squared minus something minus something. When y is negative, it's minus minus, which would be plus something plus something. So I think that's what it is. Now this. Oh, wait. I'm sorry. I was saying them backwards. This is the XZ plane, okay? XZ plane. So this would be saying Z is equal to X squared here. And this would be, at Y is equal to something positive, it would be a minus. Yeah. So, whatever your Y is coming out this way, then your Z would be X minus whatever that was. So in that sense, this line down here, the trough here, would be going right through the YZ plane. And that would be the line, looks like it might be y is equal to, no, z is equal to minus y. Okay? And so when x was constant, that would be z. If y is b, then z would be minus b. Yeah. So that would be going down there. Now, this one over here, all right, these are parabolae again, but now the parabola is in the YZ plane, okay? And here is your base one that looks like right there. That looks like to me to be z is equal to minus y squared. Doesn't that appear to be what you got there? Looking down. Okay, z is equal to minus y squared. Okay? Then x, as you come forward, a units here, x is going up in a, and if you're going back, if a was negative, it'd be going down there. So if x is a, then z would then be a minus y squared. So the minus y squared stays the same, but the x value, whatever that was, is how far up it's going. So x is going to be a minus y squared. That gives you the downward bending parabola, minus y squared, and upward moving x, the vertex is moving greater x, or if x is going negative, it's going negative. Okay. So the vertex is decreasing in the positive y direction. Here the vertex is increasing in the positive x direction. They just say increasing and decreasing. They have to say what? I think they mean vertex. Maybe the whole parabola, whatever. Okay. All right, how are we doing time-wise? 5 minutes? Okay. I think we got time for another one anyway. Now, I think I jumped a little ahead when I was mentioning before contour maps. Those are your horizontal traces, basically. That's what you get from a horizontal trace. We also call these level curves or horizontal traces. Okay? Well, they're not quite the same thing, but close to it. All right, here we have, I think, one that we saw before, or something similar to it. Rise here, depression there, rise there. Okay. Now, if we're looking at horizontal traces, if indeed this function is up here somewhere, it doesn't ever cross down here. However, this z equals c cuts it here, and if you projected that down to the xy plane, that would be the level curve alpha of xy is equal to c. It's what you get when you do z is equal to c cut across here. That's what you would get, but then you move it down to the xy plane, alpha of xy would be whatever that c would be. Okay? Actually, that better describes it as they just projected it downward. Okay? If you go up some, you'll get smaller and smaller circles until, I can't tell if these are the same height or not. This one might disappear first and that one a little bit later, but after a while you then get nothing. If you go down, your circles get bigger and bigger, and then suddenly down here, you're almost in a plane, it appears to be, or close to it anyway, and then you get below that, and then you have single circles getting smaller and smaller here until it disappears to a point and zero below that. So those are your horizontal traces, which we sometimes call your contour lines, or related to level curves. Okay? Let's get a little bit of those definitions back into play. Horizontal trace at height C, the intersection of the graph with the horizontal plane z is equal to c, consisting of the points xy, f of xy, such that f of xy is equal to c. The level curves, the curve f of xy equals c in the xy plane. So the projection of this into the XY plane, that's your level curve, that's your horizontal trace. That's why they have it listed that way. They look identical except where they're located. The XY plane, they're level curves. If they're at Z is equal to C, they're your horizontal traces. Okay. Then what a contour map does for us is this. I can't get it all on there, can I? Oh boy, close. Let's try it. Okay, right at the edge. Now this is another 2 humps, 1 depression thing. I don't know if they just twisted it around or whatever. This is Z is equal to f of xy. All right. Well, what if we wanted a single sheet, but we want to show all the elevation, or at least intervals of elevation? Okay. That then leads to, if you imagine multiple horizontal traces here, above and below the y-axis, we then project them all onto a level curve at the surface, then indeed you'll get something like this. Now typically what we do is pick your, what they call the contour interval, the distance between these values. Let's just say it's C. The distance between this and that is C, this is C, that and that is C. All those are C. So if that C was, say, 20 feet, then this would be, if this was 0 feet, that would be 20 feet elevation, 40, 60, 80, 20, 0, 20, 40, 60, 80, 100, 120. It would be close to 130 or 135 up there, okay? I just picked a number. Usually these are regularly spaced. This one would be, if this was 0, this would be at minus 20, minus 41, 60, minus 80. So a pretty deep hole there that you have, okay? But those would be your various horizontal traces. Plot them all onto one level curve, and you've got what we call a contour map. You have to identify where you are. You can't, looking at this, if you didn't have the shape here, or the shape's there, you can't look at that and say whether this is a depression or a rise, okay? They basically are the same. The way they've drawn it, you can tell, but you have to have numbers by some of those to let you know which way you're heading, okay? Now, things to note here. The flatter part of the graph is where the contour lines are further apart. Those are almost completely flat. Where the contour lines are closest together, that's the steepest part of the graph. Down there, here, that even more so. Contour lines are closer together. When you plot them on one, is it time? Oh, is that what you're saying? It is time. What sad words. Okay, we will pick up then next with, I think it's example 5. I think we got down to, but didn't get to example 5. So we will do example 5. Let's see if there's any homework exercises too. This is one long section that I have very little, I mean, it's got stuff in it, but not that much. Think you can do any of the odds, either 1 or 3 or both. Any of the odds 5 through 11. Either 13 or 15 or both. Uh, 17 or 19 or both. 19 really looks like a fun problem. Okay. Any of the odds 21 to 25. And I think probably that would be a good place to stop, because we haven't actually sketched the contour line yet, so we can stop right there. We did the vertical horizontal traces, but we didn't do contour maps. So stop at 27. You can do 27. Well, no, stop at 25. Okay, good deal. All right, next week, I think, is the last week before Thanksgiving. Is that right? I think so. Pretty close to it. But if not, it's pretty close. And you have the whole week of Thanksgiving off, sadly. We have to come Monday, Tuesday, and Wednesday, but y'all aren't coming. Okay? And then you have Thursday, Friday, everybody's off. And then I think we have one more week of class after Thanksgiving, and then I believe it's finals week, or pretty close to it. So we don't have that much time left. We really need to move as much as we can into chapter 14. I wish we could do 15 too. It just doesn't look like we're going to have much time to do it. Let's get as far as we can in 14. Good deal. Have a good weekend. Enjoy your Veterans Day. Any of you veterans? Okay, well, enjoy Veterans Day anyway. All right, good deal.